Hello there, children. Today we're going to work on problems 41 through the end of the review. Now 41 here, you deposit money into a bank and they want to know how long will it take the balance to reach $2,400. Biggest thing here is interest compounded continuously. That to me speaks to the PERT formula, which you have in your formula sheet. You divide by 2,000 and then you turn it into a log from here. You go E is the base, which means ln of 2.1 equals that exponent. You divide by that exponent and solve, and remember to put t into years. Rewrite the equation in exponential form. Remember, the base is always the base. It's all about that base, No exponents. The base is 105 of the log, or the base will be 105 of the exponential. Let's think about that for a second. And then these two things flip-flop positions. Or do your little loop, start at 105, grab the 2, and it equals 11,025. Evaluate the expression without using a calculator. Well, this one actually isn't as bad. Remember, using our power property, I can take that 3, drop it out in front. And then the ln of e, remember, they cancel out, if you recall that from our properties of logs. Because ln and e are pretty much opposites of each other. And you're left with 3. Evaluate the expression without using a calculator. I don't know what this equals. Let's turn it into an exponential. That means 6 to something equals 36. Now, 36 can be written as 6 squared, and as you know by our properties of logs and exponentials, that if two things have the same base, they must have the same exponent, hence why x equals 2. Here, find the inverse of the function. Remember, this means inverse is just turning it into an exponential and solving. Pretty straightforward there. Turn it into an exponential and solve. For x, and then you switch. Simplify the expression. This means, remember, you write it as things with perfect squares. So let's think about that for a second. Think of a perfect squares in here. Now, what we have here is 8 can be broken into 4 and 2, 40 can be broken into 4 and 10, 160, 16, and 10. Now, why do I do that? I only break them down if I can fit the biggest perfect square possible in there. So then what I do from there is square root of 4 is 2, square root of 4 is 2, square root of 16 is 4. You multiply your coefficients, and then we combine our like terms. This one has nothing to combine with. These two do, hence why I get the negative 6 root 10. Write the expression in exponential form. Pretty straightforward. There's my item. Remember that 5, my index is always the denominator of my fraction. That exponent is always the numerator. Radical form. Same rules apply, but in reverse. You could take this index, write it out there, and then that square becomes 9 squared like that. Or you can write on the outside of the whole thing. Or you can just square 9 and go, that's 81. Your choice. Doesn't matter. Remember, the index is always the denominator, and this numerator is always the power of that base, or you can put it to the outside of the whole thing. Both are equivalent. In this problem, we're going to multiply our coefficients, get 15. We add our exponents. Now, unfortunately here, the exponents don't have common denominators, but that's okay. We can make them have common denominators, which will be 12. 3/4 becomes 9 over 12. 5/6 becomes 10 over 12. And you add your exponents from there. Given something as a factor, what is the value of p? Well, remember, you can just one of two ways. You could attempt to factor that with that, or simply go, if this is a factor, x minus 5, that means I can put that 5, remember, opposite of my factor is what I would divide by, and do synthetic division. And if it's a factor, it means I have no remainder. And if I have no remainder, that p-value has to be 25 in order for 25 minus 25 to equal 0. That's a very simple way to do that. Or essentially what it's asking is, if I want this as a factor, what do I have to have as p so that I can factor that polynomial? But this is a simple way. If they give you a factor, you can use synthetic division. Find the value of the function, the vertex of the function, not value, excuse me. Well, guess what? This is vertex form of a parabola back in part of chapter 6 and chapter 5. Remember, the opposite of the number inside there is 3. The outside number stays put. It is where my parabola turns around again, or has a min or a max. Factoring this. First thing I factor, GCF, your good chumly friend. You're always going after that factor. Once I do that, I figure out what two things times each other get me 16, but add to -8. And in this case, it's -4 and -4. Now it's x minus 4, so that makes it x minus 4 squared. That would be the simplified version of it. What is the remainder when this happens, when divided by x plus 1? Well, guess what? If I'm divided by x plus 1, it means -1 is a factor. Now, the only thing goofy about this is I need a placeholder for the x squared. Why do I need that? Simply put, I don't have one. I go from x to the third to x to no x. I need a placeholder. If you don't have that, you are most certainly going to get the problem wrong. So let's think about that for a second. Now, we do synthetic division, drop the first number down, multiply, drag up, and add. Multiply, drag up, add. My remainder is 5. Write this in log form. The base is always the base. So base of this is 6, base of my log is 6, and that 2 and 36 switch positions. Or do our loop diagram, 6 to the 36, 2. 6, 36, 2. Write in log form in exponential form. Base is always the base, and these two things flip-flop positions. Or 3 to the third equals 27. Solve this. Alright, this is good old-fashioned change base formula. Unless your calculator can type that in, then kudos, you don't have a problem there. Oh, happy days, you're here again. Now, otherwise, you draw a little line there, and you go, okay, guess what? Log base 20 over log 5, or ln 20 over ln 5. Now, why do I pick ln and log? Because guess what, folks? They have things that my calculator can type in easily. So, you are good to go now for the review. Oh, happy days are here again. Oh, yeah! Go henceforth and do. Commence.